Good morning, everyone. Hope the lockdown is treating you well. Let's have a quick review on transition elements, and we shall have our introduction as well. Transition elements are those that are found in the D block of the periodic table. And we say that the D block of the periodic table lies between group 2 and group 13. We can define a transition element as a D block element that forms one or more stable ions with an incomplete D subshell. It forms one or more stable ions with an incomplete D subshell. For an element to be called transition, the stable ion that is formed must be with an incomplete D subshell. We shall find out that there are some elements that form stable ions, but their D subshells are complete. And if we have any of these elements, they do not qualify to be transition elements. The word transition itself means change. That's why we shall have one or more stable ions. They change from one. You find, for example, they have one stable ion, you have two or three, depending on the variable oxidation state of the element. Now, we have said that there are elements that form one stable ion with a complete D subshell. For example, we have zinc. Zinc is not a transition element, though it is found in the D block. This is because it has only one ion and it has a complete 3D subshell. A complete 3D subshell. We also have scandium. Scandium forms only one ion and it has no electrons in the 3D subshell. So these two elements are not transition elements. Though they are found in the D block, they are not transition elements, simply because they have only one ion and they have a complete D subshell. That is for zinc, and for scandium, it has no electrons in the 3D subshell. Electronic configurations of transition elements. Electronic configuration shows the arrangement of electrons within the orbitals that are located within the subshells. The subshells that we do have are the S, P, D, and F subshells. The S subshell has an orbital that is occupied by a maximum of 2 electrons. The P has orbitals that are occupied by a maximum of 6 electrons. The D has orbitals that are occupied by a maximum of 10 electrons. And the F has orbitals that are occupied by a maximum of 14 electrons. So in the atoms of transition elements, we have the 3D subshell and the 4s subshell as the last orbitals. And when we are filling up with electrons, we fill the 4s subshell, and then the rest of the remaining electrons are occupied by orbitals in the 3D subshells. Now, for some elements, such as copper and chromium atoms, these you'll find that the 4s is not fully filled, and then the electrons, some are transferred to the 3D subshell. The chromium atoms have one electron in the 4s subshell, and the remaining 5 electrons are going to be arranged in the 3D subshell so that each orbital is occupied by one electron. Let's not forget that the 3D subshell has 5 orbitals, and each of these orbitals is going to be occupied by one electron, making a total of 5 electrons. The copper atoms also have one electron in the 4s subshell, and the remaining 10 electrons are arranged in the 3D subshell so that each orbital is filled by 2 electrons. So from the electronic configurations, you can see that for chromium we have 5 3D 5, for S 1, and for copper we have 3D 10 for S 1. Here are some of the elements with the electronic configurations. We have titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper. As you can see, the electronic configurations of scandium and zinc are not included because they are not transition elements, or you can say they are not regarded as transition elements due to the reasons that we had earlier stated, that is, having only one ion and having no electrons in the 3D subshell, that is for scandium, and for zinc it has the 3D subshell which is full with electrons. For copper we have the 3D 10 and then the 4s. We cannot take out the fact that copper has more than 2 ions. There is copper 1 ion and copper 2 ion. And then the 3D comes about by getting an electron from the 4s to the 3D so that it can be fully stable. Ions of transition elements. All transition elements are metals. With this, they tend to lose their electrons, forming positively charged ions, which is courtesy of all metals. However, transition elements form more than one ion. For example, the common ions for copper are the copper 2 ions and copper 1 ions. For iron, it is iron 2 and iron 3. This is what differentiates them from the rest of the other metals. From this, we can say that the transition elements have variable oxidation states, and these variable oxidation states are the ones that bring about the different colors that are observed amongst the different ions. For example, copper 2 ions are blue in color, but when you count the copper 1 ions, these ones are not blue. In most cases, they are dark green, sometimes they are green. Below are some of the transition elements with their variable oxidation states. Titanium, which has +3 and +4. Vanadium has +2, +3, +4, +5. Chromium +3, +6. Manganese +2, +4, +6, +7. Iron +2, +3. Cobalt +2, +3. Nickel +2. Copper +1, +2. Due to the existence of variable oxidation states among the transition elements, there is need that the names of their compounds must have the oxidation are included within the name. For example, manganese 4 oxide, meaning that Manganese used an oxidation number of 4. We have copper 2 carbonate, whereby the copper that was used was copper 2 ions. So during the formation of ions, electrons in the 4s subshell are lost first, followed by the 3d electrons. And this is basically because the electrons in the 4s subshell are easier lost compared to those in the 3d subshells. Therefore, that's why the electrons in the 4s are easily lost, or they are lost first, followed by those in the 3d subshell. Below are the lists or examples of atoms and their ions. And basically our major interest in is you observing the partially filled d subshells present in these ions. As earlier described in the definition of transition elements, saying that there are those that have partially filled d subshells.